In the last video, we mentioned the concept of an orthonormal basis, but what is a basis? Well, in short, a basis for a vector space is a set of linearly independent vectors that span that vector space. But what does that mean? Well, like in our last video, let's look at R2. We'll put an R2 up in the corner here, just so that we don't forget what vector space we're working in. And we'll also draw our standard basis for R2, that being E1 and E2. One technical way to define linear independence of a set of vectors is that in order to achieve the zero vector by summing together every vector in that set, you need to multiply every vector in that set by 0. No other scalars work. This can be a pretty strange and odd-seeming definition, however. So let's take a look at our vectors here. Are they linearly independent? Well, as I've said, they are a basis, so yes, they would be linearly independent. So let's take a look at them in their column vector forms to try and understand where that's really coming from. Like in our last video, we can write E1 and E2 as these two column vectors. As previously mentioned, to test for linear independence, we need to see how we can add E1 and E2 together to create the zero vector. Editor's note that 0 is the zero vector, not a scalar 0. When adding our two vectors, we can generalize the linear combination as E1 times some scalar A1 plus E2 times some scalar A2. This would leave us with the vector A1, A2 by vector addition. What's the only way to get the zero vector from this? As you can see, the only way for our vector A1, A2 to be the zero vector, both A1 and A2 must be 0. Since these are the only scalars that work, our vectors are linearly independent. This condition is most definitely visually shown, as you might have seen. This is because these vectors are orthogonal. Let's visualize it this way. Take E1. No matter how you stretch it all the way to the right or all the way to the left, you'll never go up any amount. Similarly with E2, no matter how far you stretch it up or down, you'll never go any bit to the right or left. You cannot create one vector out of the other. Now, there was another piece to that basis definition, and that was that the vectors span the space. So, what does that really mean? Well, a set of vectors spans a vector space if any vector in the space can be expressed as a linear combination of the vectors in the set. So, what does that mean? Well, take some arbitrary vector v. In 2 dimensions, it has 2 components, v1 and v2. This vector can point anywhere. That's how it's arbitrary. And for the sake of example, let's just say that this vector is the vector 3, 2. In other words, it points right 3 and up 2. Well, in order to get right 3, you multiply E1 by 3, and to get up 2, you multiply E2 by 2. So, in order to construct V, you would simply add 3E1 and 2E2 to end up with 3, 2, or V. So, in order to get to V1, V2, you just multiply E1 by V1 and E2 by V2 and add them together. So, any vector can be expressed as a linear combination of E1 and E2. Therefore, since E1 and E2 are linearly independent and they span the space, they form a basis for that space.